Good evening, everyone. This is Power Plant System Engineering course being conducted under the NPTEL program by Department of Mechanical Engineering, IIT Guwahati, and we are finally at the last live session of this course, which basically is a course concluding session. So here we will see briefly the topics that have been covered in the whole timeline of this course. Okay, it's a 2 hour session, so we will try to touch upon the topics in brief so that we can recap the whole course and see it as a whole. Okay. Instructor for the course is Professor Niran Sahu from Department of Mechanical Engineering, IIT Guwahati, and I am a teaching assistant, also a research scholar here at Department of Mechanical Engineering, IIT Guwahati. So, contents of today's discussion are this way. So it was a 12-week course. Here, the major thrust was on vapor power system. Okay. Then we saw gas turbines related power plants. And then there was third set which was on hydro and renewable energy power generation system. Right? So we will start with today's session, but before that let's wait for a couple of minutes before we start. Okay. So I believe I can start with the session. So first we had week one where we reviewed our basic thermodynamics knowledge. So some broad topics that were covered were: one was your first law of thermodynamics, which basically is the law of conservation of energy. Then we saw steady flow devices. So steady flow devices were discussed from the perspective of your parts of vapor power system, right? Where you encounter different steady flow devices. So be it your turbine, be it your pump. Okay. So this discussion was done on your steady flow devices, right? So Saranya, this is course concluding session. So I'll be briefly discussing the all the topics that have been covered in this timeline of this particular course. So I have just mentioned it. So at present, I'm discussing week number one's content. So this is a 2 hours session, right? Then we saw second law of thermodynamics, right? So which basically is, if you see the Clausius statement, right? This comes in your second law of thermodynamics, right? After that, we saw our ideal cycle, that is Carnot cycle, right? So I'll draw the PV diagram for your Carnot cycle. And this is your temperature entropy diagram for same cycle. So if you see your TS diagram, 1 to 2 is your isentropic, right? 3 to 4 again is your isentropic. Yes. Okay. If you want to ask something, you can ask. So this basically is your Carnot cycle, right? Heat addition, heat rejection, right? So this has been discussed in your week one. Then exergy, concept of exergy has been discussed, right? So exergy basically is the maximum useful work that you have in your hand, right? And how do you calculate your exergy? Based on your dead state, right? Dead state in most of the cases is your environment, the conditions at which your environment is, right? So this is basically your discussion on exergy. So this is a course concluding session, okay? And then related to your exergy only, or second law efficiency has been discussed, right? So these were the brief and broad topics that were covered in your week one. Then is your week two, right? So week one was basically about revision of your basic thermodynamics concepts. First of thermodynamics, second law of thermodynamics, what is exergy, right? What is a system, what is an open system, what is a closed system, what is a boundary of a system, what are adiabatic systems, so all this. Then from your week two, you start with your vapor power systems. Okay. So in vapor power plants, topics I have mentioned is introduction to vapor power plants, performance indicators, Carnot cycle, modeling of Rankine cycle, effects of boiler, condenser, and pressure. All right. So vapor power plants, right? What are the components of a vapor power plant? You have your boiler, you have your turbine, you have your condenser, and then you have your pump. Okay. So these are the basic four parts of a vapor power system or vapor power plant. Right? Then how do you define the performance of your vapor power plant? So different parameters have been mentioned and discussed. Okay. So one is your efficiency, which is your W net by heat in, right? And what is W net? W net basically is your W turbine minus W pump. Okay, this is your W net. Then there are other ratios like work ratio. Okay, which basically is your W net by W turbine. Similarly, there is back work ratio, that is W pump by W turbine. So all these parameters have been mentioned. Okay. Then Carnot cycle, because has been discussed here also. So I'll take help of this only TS diagram, right? So this basically is Q in, right? Q out, right? This is your turbine work. Here you give work. W pump. From here you get work. This is WT, right? So this is your Carnot cycle. Then the most important topic is modeling of your Rankine cycle. Right? So if you see the Rankine cycle diagram, now there are two cycles. One cycle is from 1 to 2 to 3 dash to 4 dash, then to again 1. This is one cycle. Another cycle is 1 to 2 to 3 to 4 to 4 dash to 1. This is another cycle. So what is the difference between these two cycles? First, this is your Carnot cycle, okay, and this is your Rankine cycle. Difference is that in your Carnot cycle, so 2 to 3 basically is this path where you are condensing your steam that is expanding from your turbine. Okay, this is your turbine. This is your boiler. Here, this is your condenser. This is your pump. Okay, so if we move according to Carnot cycle, in that case, the state at which you'll have to pump your condensate is this. So this is not a saturated state. Okay. So in that case, to handle a mixture becomes a bit tedious task, right? So for to overcome this limitation, what we do, we don't limit the condensation to 3 dash point. We extend it further to zero point 0.3. So in that case, your condensate becomes totally saturated. And after that, we pump it to our position 4, right? Then from 4 to 4 dash, we do feed water heating, right? And 4 dash to 1, the boiler comes into picture. So this basically is your Rankine cycle. I hope there's no doubt in it. Then effects of boiler and condenser pressures. So if you increase the boiler pressure, so I won't draw the diagram for this, but if you increase the boiler pressure, in that case your efficiency increases. And if you decrease your condenser pressure, right, the pressure at which you are condensing your steam that is coming out from your turbine after expansion. So if you decrease this pressure, in that case again your efficiency increases, right? So pressure should increase in case of boiler and decrease in case of condenser if you want to improve your efficiency of your Rankine cycle. So this is your week 2. Till this point, if there is some doubt or if you want to ask something, you may please. Then we shall see week next week, next week's content. No doubt, Saranya?
No doubt, sir.
Okay, okay, thank you. Then is your week 3. So In week 3, the focus. So in week 2, we saw we were introduced to Rankine cycle. Now in week 3, what we are doing is we are modifying our Rankine cycle. And what is the reason for modification of Rankine cycle? The basic reason is we want to increase the efficiency. Right? So topics like, so this is performance improvements, right? That is why we are modifying our Rankine cycle. So how do we do this? So superheat cycle, one is superheat cycle, then is reheat cycle, then supercritical reheat cycle, then is regenerative open feed water heater, then at last I have written binary vapor cycle. Okay, so we shall see this. Okay. So if you see your superheat cycle, superheat. From Rankine cycle, when you get the steam, that is in saturated state. Okay. But then here, what you do is you further heat it so that this attains superheated state. So this basically is your Rankine cycle. Right? Now superheated cycle is like this. Right? Here you are extending it to here and here. Right? So this basically helps in increasing your efficiency, right? Also, this superheating improves the dryness friction, right, of your steam. So that is good for your turbine, the proper functioning of turbine, right? This is your superheat cycle. Then in your reheat cycle, so in superheat cycle, the expansion of steam takes place in one go, right? So from 1 dash to 2 dash. This is your turbine expansion. This is your reheat cycle, right? Super heat cycle. So let's write it as 2. This is 2 dash. This is 3. This is 3 dash 4, 5. Next this one. So 1 to 2 was your superheating, right? Then 2 dash to 3 is your reheating. Okay. So from 2 to, ideally, if you see for your super heat cycle, the path would have been this 2 to 3 double dash. But what we do in your reheat cycle, we let our steam to expand till 2 dash point, and from there again we reheat this steam. Okay, and from there it reaches at another state 3, and from there we let it expand fully. Okay, 3 to 3 dash. So this is your reheat cycle. So what is the advantage of reheat cycle? The steam quality at the exhaust increases, right? So this is your reheat cycle. Then you have your supercritical reheat cycle also, right? So here what happens is that you don't have any intermediate state, right? From your liquid saturated state, your steam steam state attainment is direct, right? So there is no mixture state that this transition has to see. So this basically is your supercritical reheat cycle. All right. So its diagram is like this. So this basically is the path of a supercritical reheat cycle. Then is your regenerative cycle. So what happens in your regenerative cycle? In regenerative cycle, what you are doing is the feed water, right? The feed water that you are eventually going to give to your boiler. So you preheat it using the steam that is expanding from the turbine. So in the midway, you take some steam from your turbine that is expanding, and this the heat from this steam is being used to heat your feed water. Okay, so there are two types of feed water heaters. One is open feed water heater, one is your closed feed water heater. So I'll just draw maybe one such feed water heater, regenerative cycle, sorry. So let me draw the diagram first, then I'll just explain it. So what happens here is, if you see the point 2, right? is 7. Let's say this is 7 dash. Okay. So 7 dash to 1, 7 dash to this point is your boiler. Then this is superheating up to point 1. Okay. Then 1, 2, 3 is your expansion of the steam. Right. But in the midway, you see at point 2, you're taking some steam from point 2, right? And it's reaching at point 6. So what basically is the purpose of this action, right? So this basically is heating your feed water that you have pumped from 4 to 5, right? And then it is reaching at point 6 with the help of this heat from this steam, right? If we had not used this feed water heating system, right? In case we would have to take we would have to take our working fluid from point A to point 7, right? That would have caused expending more fuel, right, to reach to this state. But here what we did, we used the heat energy from our steam that we took from point 2, right? So this basically is your regenerative cycle, and this is your open regenerative cycle, where your steam that you are taking eventually mixes with your feed water heater, with your feed water, right? In your closed regenerative cycle, which is closed, right, or closed feed water heater, in that case your this steam doesn't mix with your feed water. Okay. So this basically is your regenerative cycle. Okay. All right. Then one topic is your binary vapor cycle. So binary vapor cycle is nothing but there are two different cycles, right? So one is your topping cycle, one is your bottoming cycle. So your topping cycle works at high temperatures, and your bottoming cycle works at low temperatures, right? Yes. So this is your binary vapor cycle. Then is your week number 4. So this is on turbines or rotodynamic machines machinery. So turbine again is a very important topic from where we extract our work. Okay. So just give me a second. So there are broadly two types of turbines. One is your impulse turbine and one is your reaction turbine. Okay. And what is the difference here? So we will see the difference by means of diagram. Okay. So in your turbines, there are compoundings also. Okay. So first, let's see. Your 3, 4. Impulse turbine. Avoid this way. So this is your nozzle. So here you have blades. So if you see your pressure drop, here the pressure drop is in your across your nozzle only, and there is no pressure drop across the blades. And what about the velocity? So this is your pressure, this is your velocity. Okay. So velocity at blades your decreases, right? Across the blades your velocity decreases. So this is your basically impulse turbine, right? But if you see your reaction turbines, so there is pressure drop across your moving blades also, right? So fixed blades in case of reaction turbines work as nozzles only, right? Where you have your velocity increase and the pressure decrease. So reaction turbine basically is mixed section of your uh, pressure drop and your this velocity drop, right? So these are your fixed blades, moving blades, fixed blades, moving blades. Okay. So what is the how the pressure behaves here? Sorry. So if you see a pressure, So it will behave like this. It will drop in fixed blades. It will drop in your moving blades. It will drop in your fixed blades. It will drop in your moving blades. But if you see the above case in your impulse turbines, across the blades, your pressure doesn't drop, right? And this difference also eventually uh, gives rise to one term, that is degree of reaction, right? So degree of reaction basically is enthalpy drop because of this across, because of this your pressure drop, and then in totality, I believe. Yes. So enthalpy drop in your moving blades, and then enthalpy drop in your whole stage. So this basically is your degree of reaction, right? This is your pressure. And what happens to your velocity? So velocity is like this. In your fixed blades, it will increase. Here it will decrease. Here it will increase, and here it will decrease. So this is the trend of your velocity. Okay. This obviously is your distance. Distance, right? I hope you understand. This is like one shaft, and in this shaft you have your blades in this shaft, right? Some blades are fixed. At some section there are fixed blades. At some section there are moving blades. Then fixed blade, moving blades along the circumference of your shaft. So these are impulse and reaction turbines. So there is compounding also has been taught. So compounding, I believe I won't discuss, but this basically is, if you understand the impulse and reaction turbine, then you will be able to understand compounding also, right? Okay. So this is your turbines, weak for turbines. Then week 5 focuses on, so this still talks about turbines, but then nozzles have been introduced, right? So now let's see nozzles. Yes. So nozzle action. This is your week 5. Week 5 talks about nozzle action. So what is nozzle action? So whenever the velocity of fluid increases, right, across some, just give me a second. Yes, so I was talking about nozzle action. So whenever your fluid passes through a conduit, right, or some pipe, and its velocity increases, that basically is your nozzle action. So if you see a pipe, right, or conduit where the area is decreasing, right, the cross sectional area is decreasing, in that case what will happen is for your subsonic flows, I believe you understand what is subsonic. Subsonic means where your Mach is less than 1. So in that case the velocity increases, right? And if this is a diverging section, if it is a diverging section for Mach less than 1, in that case your velocity will decrease, right? That is your diffuser action. But here we are concerned with nozzle action. So this is your nozzle action. Now there is one more case of nozzle action also, which basically is when your Mach is greater than 1. What happens is when your Mach is greater than 1 and you have a divergent section, in that case the velocity further increases. So when the Mach is less than 1, in that case a converging section will lead to nozzle action. When Mach is greater than 1, in that case a diverging section leads to nozzle action. Then a CD nozzle, convergent divergent nozzle. So I'll draw a CD nozzle first. Okay. So this is the direction of flow. Then let me draw the pressure variations. So this is basically your throat. Maybe I should just explain this one. This is your throat. This is your entry of nozzle. This is your exit of nozzle. Right? This is A dash is your B dash, C dash is your exit. So what drives the flow basically is the pressure difference, right, between your entry and exit. So as we keep on decreasing the back pressure, right, the pressure at the exit, in that case, your flow rate starts increasing, right? The mass flow rate in the nozzle starts increasing, right? But there is a point beyond which the mass flow rate can not increase. And what is that point called, or the condition called? That is called choked condition. So what is a choked condition? Choked condition is basically when the flow mag at your throat reaches at Mach 1. Okay? So this basically is your choked condition. In your choked condition, the mass flow rate will be maximum. And if you further increase the back pressure, this will further keep on expanding. Right? Let's say your flow is expanding, right? And at some point here, so this is expanding, right? So at some point here, the pressure that you have at this point is less than the back pressure, right? In that case, what happens is this becomes an overexpanded case, right? And so if the pressure here is low, in that case, that means flow cannot take place, right? So some other mechanism has to take place here so that the flow takes place. So that is another story. But for our purpose, to this point is sufficient, right? That is your expanded case. But if your exit pressure is still greater than your back pressure, in that case, this becomes an under expanded case, right? So there are two cases. One is over expanded, and one is your under expanded, and one is your design case, design condition. What is your design condition? Your design condition is when your exit pressure is equal to your back pressure. So that is your basically design condition for a nozzle. Okay, so this is about nozzles. Then is your week 6. So week 6 basically is on your boilers or steam generators, right? So parts of steam generators are like economizer, boiler, superheater, reheater, air preheater, right? It has a steam drum. What is a water tube boiler? Parts of water tube boiler are this is your week 6. Week 6 is on boilers. Right? So you have your economizer, right? From there you have your steam drum, then you have superheater, right? Then you have reheater, then you have induced draft fan. Right, superheater basically is this when we have discussed these cycles, right? These modification of Rankine cycles. So this 1 to 1 dash basically is done by a superheater, right? Then 2 dash to 3 is done by your reheater, right? And before that 6 to 1 is done in your steam drum. Okay. So these basically are the components of a water tube boiler, right? So this is about week 6. This is about boilers. Then is week 7, right? Before starting week seven's discussion, we will take a short break. All right, a short break of about 5 minutes. Then we will continue with the session. Okay, so let's continue with the session. So, in your week 7, so till now, up to week 6, we have discussed review of thermodynamics, then Rankine cycle, modified Rankine cycle, then turbines, then nozzles, right? And after nozzles, boilers have been discussed, steam generators, basically. Then we come to week 7's content, which basically is your fuel that is used in boilers, okay, to heat your working fluid, in cases water, to get steam. So coal is one important fuel that is used in your vapor power plants. Okay, so coal has been categorized based on its quality, right? So high grade coal is anthracite and low grade coal is lignite, right? Then coal analysis gives the different components of coal. So there are types of analysis. In coal analysis, you have proximity analysis, then you have ultimate ultimate analysis. So in what do you get in your proximity analysis? So this proximity analysis gives you mass percentage of your fixed carbon that is present in the coal, then volatile matter that is present, moisture and ash. Ultimate analysis is more detailed, which gives you elements also that are present in different elements that are present in your coal, right? Like carbon, hydrogen, oxygen, nitrogen, sulfur. It gives the content of moisture and ash also. Then one important topic is about heating values, right? So heating value basically is the amount of energy that when we heat coal, the amount of energy that we get, right? But when the combustion takes place, one of the products is water also, right? So based on the state of this water, we define two values. One is your HHV, that is high heating value, and one is your low heating value. So what is high heating value and what is low heating value? So in your products, if your water is in gaseous state, that is it is steam, which means that energy has been used to convert it from liquid to gas, right? And there is another case where this water is in the products only, is in liquid state. So if it is in liquid state, that means this energy that has been expanded to convert into gaseous state in one case. This is case one, okay, and this is case two. So in case one, the some amount of energy has been expended to convert water into gaseous state, but in case two, this energy has been saved, right? So this energy uh, adds up to the energy that you have available from the coal after the combustion takes place, right? So in that case, the case 2 becomes a high heating value, right? So the saved energy gets added, right? And low heating value is because some amount of energy is expended in converting H2O to gaseous. So this is your high heating value and low heating value. Okay. Then is your fluidized bed combustion, right? Fluidized bed combustion, combustion temperature. So fluidized bed combustion is mostly used, okay, in your boilers. So there it has fluidized bed air distribution grid, cyclone separator. So fluidized bed basically is something like this, right? Something like this. Here you have bed, right? Here this is your bed. Here this is your here you have your cyclone separator, something like this, which eventually comes here over. So this is your fluidized bed. From here you get air, right? So in fluidized bed you have your coal, right? From here comes your air. Then one important, this is cyclone separator. So one important thing about this fluidized bed combustion is that you can do desulfurization. Desulfurization. So the combustion products you get, you can do desulfurization of those combustion products so that because products of sulfur are harmful for the environment, right? So from that perspective, yeah, you can do desulfurization of fuel. And how you do that is by adding calcium carbonate here in the fluidized bed. Okay. So this mixes with your sulfur dioxide and gives rise to calcium sulfate, which eventually is captured. Okay. So this is your fluidized bed combustion. All right. So this is basically about week seven's content, where the fuels have been discussed. Okay. Before this, we discussed boilers. Week 7 is on fuels. Then week 8 is the last week on your vapor power system. Okay. To condensate feed water system, direct contact condensers, surface condensers, closed feed water, open feed water, dry cooling tower, wet cooling tower. Okay. This basically is your condenser, this is your feed water heater, and this is your cooling towers. Condensers are to condense your uh, steam that is coming or exiting from the turbine, right? Feed water heater, I have told in regenerative cycles how we do the feed water heating, right? Open feed water heating and closed feed water heating. I hope you remember in your regenerative cycles in modified Rankine cycles, right? And cooling towers. What is the purpose of cooling towers? So, how is the steam condensed in the condenser, right? So, if you imagine a shell and tube type of system, right, where either in shell or either in tube, in one of these two, you'll have circulating water, right? And then also, uh, if you have in shell, if you have your circulating water, in tube, you'll have your steam, right? So this way, the energy, the heat gets transferred to your circulating water, right? And your steam gets condensed. Okay, but your steam gets condensed, and the temperature of circulating water increases because this heat is eventually going to your circulating water, right? Now, if you want the same circulating water to be used in condensing the steam, so what do? You take help of cooling towers. Okay, so there are two types of cooling towers. One is your dry cooling tower, one is your wet cooling tower. So what happens in your dry cooling tower is basically the air is you blow the air across the this your water, right? That you want to cool down, the circulating water you want to cool down, and this air basically takes away the heat in the form of sensible heat. This takes away the heat. So this is your dry cooling tower. And in your wet cooling tower, so wet, if you see from wet, you can take idea that evaporation is also involved. So evaporation also helps in taking some amount of heat from this circulating water. Okay, so this basically is the difference between your dry cooling tower and wet cooling tower. And if you see your direct contact condenser and surface condenser, so surface condenser basically again is you take example of a shell and tube type of system, right? So this way through surface the condensation takes place, right? And in your direct contact condenser is where your steam is directly coming in contact with your circulating water, that is condensing the steam. That is your direct contact condenser. So one example of direct contact condenser is where you spray your circulating water, right? where you spray your circulating water in a chamber where there is steam that you want to condense. You can imagine it this way. So that basically is your direct contact condenser, right? So this is your condensate feed water system. So this was about week 8. Then is week 9. So week 9 is on gas turbines. So gas turbine works on your Brayton cycle. Okay, so I'll draw this. And then regeneration, compressor intercooling, combined cycle power plant, aircraft propulsion system. Gas turbines are readily used in your aircraft propulsion system. Okay, so turbofans, if you see turbojets, okay, turbo props, these are types of engines. Turbo shaft, all right. Then there are ramjet also, scramjet also. So these engines work on your Brayton cycle. So the PV diagram for your Brayton cycle is this way. And your TS diagram is this way. P here is constant pressure process. And this is constant entropy process. Okay. So P equals to C, P equals to C, S equals to C, S equals to C. So these two are constant entropy processes and these two are constant pressure processes. Right? So this is your Brayton cycle used in your gas turbines. And what is regeneration? Regeneration basically is preheating your compressed gas. Okay. Yes. And then compressor intercooling is there, where you cool down the air that you have compressed in your compressor. Right? So gas turbines basically are like this. If you see your gas turbine, you have inlet, compressor, combustion chamber, then turbine. Inlet or diffuser, you can say. So it is like this. This basically is the flow diagram of a gas turbine. Then combined cycle power plant has been discussed. What is combined cycle power plant? Combined cycle power plant basically is when you have at one place your gas turbine setup, right? And at another place you have your vapor power plant setup. And what you do is the exhaust from your gas turbine that is coming. So this exhaust from your turbine that is coming has some heat still in it, right? So this heat can be used to convert your water to steam in your vapor power plants. So this basically is your uh, combined cycle power plant, right? Where you are using two different setups altogether. Okay, so this is about your week 9, gas turbines and combined power systems. Then week 10 to 12 are on your renewable energy sources and then energy storage. Okay, so hydroelectric power plant, hydraulic turbines like Pelton turbine, Francis turbine, propeller and Kaplan turbine. Then wind energy has been discussed. Okay, so hydroelectric power plant basically is you are using potential energy of water, right? So this is the basic idea behind hydroelectric power plant. And the turbines that are used are Pelton, Francis, and Kaplan, right? So when is Pelton used? Pelton is used when you have low discharge, right? When you have medium discharge, you used Francis, and when you have high discharge, you use Kaplan, right? So these turbines also have modes, okay? The impulse and reaction modes. So the impulse and reaction turbines that we saw in the vapor power plants. So this is the same The nature is same, right? Of impulse and reaction modes. That is same. Okay. Then there is direction of flow that is there in different turbines, right? So here the direction is tangential. So how we differentiate between these different turbines, right? In your Francis you have radial, and in your Kaplan or propeller type of turbine you have axial flow of water, right? So these are basic differences between your Pelton Francis and Kaplan turbines, right? Okay. Then is your wind energy, right? For which you use wind turbines. So wind turbines also are horizontal axis wind turbine and vertical axis wind turbine, right? Yes. So vertical axis wind turbines are not suited when the winds are very heavy, right? It cannot take heavy winds. On the other hand, your horizontal axis wind turbines can take heavy winds, right? Then there is power that you can generate from a wind turbine. So there is expression for that is given, which is you want to calculate the power that is generated in the wind turbine. So you can do it with this Vi minus V exit. So Vi is the inlet velocity, VE is the exit velocity. Rho is density, A is the cross section area, and V subscript T is the velocity that is within the turbine. So across the turbine when your wind passes. So in that section, what is the velocity? So this velocity also we calculate from some uh, uh, mathematical expressions. We can find out this velocity. Okay. Then there are expressions for torque also, right? The torque that is produced in your wind turbine. So all this has been discussed in this week's content. So this was on your first hydroelectric power plant and then wind energy, week 10. Then week 11 was on your ocean waves and tidal energy. So though this was on ocean waves and tidal energy, then there was one more thing here that was based on the temperature differences, right? The insolation that the oceans receive from your sun, right, in the form of radiations. So what happens is at your surface, the temperature is higher, and as we go towards, as we go deeper from the surface of ocean, the its temperature decreases, right? And this causes a temperature difference between what is at some depth and what is at the surface. And this temperature difference can be exploited somehow to have the work requirements. Okay. Then is your tidal energy. So tidal energy basically is the tides that the oceans witness. So this has to do with the motion of your moon with respect to your earth, right? The lunar cycle, the solar cycle, and the earth and the relation, right? So that is your tidal energy. So during high tides, what we do is during high tides, so we create a dam during high tides. In the dam, we fill water, and when there is low tide, during that time we flush this water, right? And we attain the work, right? So this high tide and low tide. So the time durations have been given in your lectures, right? So you can refer to that. So that will give a proper idea. It's how the tides work, what are high tides, what are low tides, what is spring, what is neap. So all this has been discussed properly. Then is your geothermal energy, right? So geothermal energy basically is the hot magma that is present in our earth, right, at depths. So this heat can be utilized to run our power cycle, right? So this basically is your geothermal energy. So there are different systems like vapor dominated geothermal system and liquid dominated geothermal system. So all this has been discussed in this week's content, right? Ocean, yes, ocean waves, tidal energy, geothermal energy. So this has been discussed in week 11's content. Then the last week is on your energy storage. Okay, so broadly there are two types of energy storage systems have been discussed. One is your electrical storage, so in form of electricity, and one is your thermal storage in the form of heat, right? So in your electrical storage, there are further subdivisions like electrical mechanical energy storage and direct electrical storage. And in your direct electrical storage come batteries and superconducting coils. And in your electrical mechanical energy storage comes your, so this comes, these two come under electrical mechanical energy storage. This is a recent, yesterday only we discussed this. So pumped hydro storage basically is when you have excess energy, then you use this energy to pump up the water to some height so that it attains some head. And when there are peak load requirements, during that time you take help of this pumped hydro energy that you have stored. Okay. The same way there is compressed air storage. So the excess energy that you have when the demand of energy is less, in that case the excess energy that you have, so this can be used to run a compressor that will compress your air, right? So this is a form of stored energy which again you can use when you have peak load requirements. Okay. So this basically is your compressed air storage system, right? Then is a pressurized water sensible energy storage. Pressurized water sensible energy storage basically is in a vapor power plant. At times you have excess steam, so that steam is not required because the load requirements are less. In that case, you take this steam to accumulators, right? Where this steam gets condensed, and at peak loads, this again is used at some small peaking through some small peaking turbine. We use this steam that is present in the accumulators, and this way we can store this energy, excess energy, right? And there are other energy storage systems also, miscellaneous some energy storage systems, right? Like magnetic energy storage, chemical reaction storage. So all this has been discussed in this week's content. So this was it about this course, power plant system engineering, right? It was a, so I'll conclude then this session. So we have come to the end of this session. So I'll conclude this. So it, the course is a 12-week course. So we started with the review of thermodynamics in week 1. Then from week 2 to week 8, we discussed vapor power systems, where we discussed different components of a vapor power plant, right? So we started with Rankine cycle, right, and how we can modify Rankine cycle to improve its efficiency. Then we saw turbines, right, that is used to expand steam and then eventually generate electricity. From there onwards, we saw nozzles. We discussed nozzle action, right? Nozzle action we discussed, and after that, we also discussed the condensate feed water system, where we discussed condensers, right? And then we discussed the circulating water and the cooling towers we discussed, right? And also regenerative cycles, where we can take uh, help of steam, right, to heat our feed water. Okay. Then we also saw the fuels, right? How the combustion in the of the fuels in the boiler setup takes place. We discussed it. We discussed also boilers, right? So this was about your vapor power system. Then briefly in 1 week we discussed the gas turbines. So gas turbines are majorly used in your aircrafts, right? So which works on Brayton cycle. Then from week 10 to 12 we discussed renewable energy sources, right? like hydroelectric energy and wind energy, geothermal energy, right? Then ocean temperature difference energy, ocean waves, tidal energy, right? So all this we discussed in the hydro and renewable energy storage systems. And eventually in the last week we saw the different energy storage systems. So this was it about this course, power plant system engineering. Okay, so I hope this course has been a learning experience to you guys. And at this point only, I'll take leave from you. And I wish you luck for your exams. The exam that you are going to take for the certificate of this course. All right. Thank you.